Hello everyone, my name is Marcio Ozorio and I am a master's degree student at PUC-Rio. I'm going to present my research paper, Rheology of Cyclopentane Hydrates, formed in Water-in-model Oil Emulsions. My advisor is Monica Nakashi and the co-authors are Gustavo Sandoval, Paulo Mendes, Adriana Teixeira and Leandro Valim. The agenda of my presentation is a brief introduction of the subject and the motivation of my research. Then I'm going to show the methodology that I used during all my experiments. I'm going to discuss my results and present the final remarks. So, what are hydrates and how are they formed? Hydrates are crystalline compounds formed basically by water and small gas molecules, such as methane and ethane. They need to be submitted to high pressures and low temperatures to be formed. In such conditions, gas molecules are trapped and kept by water-hydrogen bonds. Well, CP is a hydrate formation agent, and as I'm using atmospheric pressure in my experiments, I need this compound to stimulate the formation. Also, the hydrate formed by CP molecules is very similar to the one formed in the oil and gas production. We have basically four steps in the hydrate formations: water entrainment, hydrate growth, agglomeration, and plug. Because of the conditions, the mix of water and gas starts by creating small crystals which are deposited at the walls of the pipes, and each crystal quickly agglomerates with the others, creating beds that accumulate in a way to form a big plug of hydrate. The majority of the oil and gas production in Brazil is at offshore fields, and so the production has to go through many kilometers of pipelines under harsh conditions. Such environments are ideal to the hydrate formations, which leads to hydrate plugs that cause pipeline blockage, production interruption, and therefore money loss. Although there are many techniques that already perform mitigating this problem, they are usually very expensive and take a long time, which is not that good for the industry. So it's very important to study and understand the hydrate's mechanical behavior in order to prevent their formation. Now I'm going to show the methodology that I used for all my experiments. And the first step is to prepare the emulsion. First, I mix the primal oil, the ionized water, and spun 80 for 5 minutes and 10,000 RPM. After that, I add CP and mix for 3 minutes and 6,000 RPM. CP is added after the first mix because it's very volatile and we want to reduce the mass loss. I'm using 30% weight of water, 23% of CP, and 1.4% of surfactant. The rest is composed by the primal oil. All my emulsions have a minimum stability of 72 hours, which is great, because all my tests have a maximum duration of 24 hours. All the experiments were conducted by the rheometer Física MCR301, and the geometry Ruthen was used in order to minimize the wall slip. After the sample is prepared, it is loaded inside the geometry cup and the heat treatment starts. We can see the 7 different steps of this treatment at the graph on the center of the slide. The first step is decreasing the temperature from 20 degrees to 1 degree. When we achieve the 1 degree temperature, we apply a shear rate for 10 minutes. And after these 10 minutes, we decrease the temperature again until the temperature of minus 12 degrees, which we keep at this temperature for 40 minutes in order to induce the nucleation of the hydrates. After that, we increase the temperature again to 1 degree and we start again to apply a shear rate. And at this point, we start to analyze the viscosity and the hydrate formation. All the data that I'm going to show here started to be analyzed when the 1 degree temperature was achieved. In that example, I performed the same test for different samples at different days. The negative temperature to induce the hydrate formation was -12 degrees, and the shear rate applied was 0.1 seconds -1. We can observe that both tests has a good repeatability, which was exactly as expected. Also, it's important to notice that the growth time, which means the time to achieve the maximum viscosity, was around 30 minutes. For this shear rate, the final viscosity was more than 1,000 times greater than the initial viscosity, indicating a great amount of hydrate formed. Here we have a figure that shows the behavior of the viscosity by time for 4 different shear rates after the temperature reached 1 degree. Again, all the parameters were kept constant, and as we can see, the lower the shear rate, the higher the viscosity, which indicates that more hydrate was formed. We basically have two forces that could explain this phenomenon: reconstruction force and shear force. After some time, the reconstruction force are able to maintain a balance with the shear force. We can observe that mainly for lower shear rates like the gray and the green curves, there is a fluctuation of the viscosity value, and that's where we can confirm that the hydrates are being broken and reconstructed by the force over and over again. Despite there wasn't a great increase in viscosity for 100 seconds -1, it could be visualized at hydrate formation at the upper part of the rotor after the end of the experiments, and I'm going to show some hypotheses at the next slide. The hydrate formed had a porous and hairy morphology, which usually happens because of the surfactant, span 80 in this case. This morphology could induce the rheometer jamming and also the apparent slippage. This structure leads to lighter hydrates, and when it's applied higher shear rates, the hydrate tends to go up to the rotor of the geometry, affecting the viscosity measurement. And that's why the viscosity curve for higher shear rates doesn't indicate the hydrate formation. You may ask, but as you have kept the temperature in -12, isn't there any ice influence in the viscosity? After the heat treatment, all the tests were conducted at 1 degree in order to avoid the combined effect of the hydrate with ice. So, at this figure, I'm comparing two tests performed with the same shear rate. The sample of the red curve had CP, and the sample of the purple didn't. With these results, it is possible to see that for the sample without CP, there was no increase of the viscosity, which means that no hydrate was formed. So, we can assume that when the positive temperature was achieved, or no ice was present, or its presence didn't lead to a viscosity increase. Finally, we can conclude that the lower the shear rate, the higher the viscosity reached, and for lower shear rates, the breaking and reconstructing force are more evident, which can be observed by the fluctuation at the final viscosity. Also, it is possible to observe a shear thinning behavior on the experiments, because the viscosity was decreased when the shear rate was increased. And despite the fact that was observed hydrates at the end of the experiments, the increase of viscosity for high shear rates, such as 100 seconds -1, was minimum, probably because of the morphology of the hydrate formed. And finally, when the CP was not used, no hydrate was formed, and no significant ice influence was observed. I would like to thank the government financing entities, CAP and CNPq, the government company Petrobras, the University PUC-Rio, and the lab Rheology for financing this research. Thank you for your time and attention. If you have any doubt or question regarding the paper or the presentation, Please just let your questions at the comment box below. Thank you.